Today we will discuss a method to construct transitive closure of a relation. This is an algorithm which is called Warshall's algorithm, and we will see that it makes computation much easy. However, before we go to Warshall's algorithm, we will just recall some of the ideas that we have discussed in the previous lectures. Now, our starting point again is a set A and a relation R on A. That is, R is a subset of the Cartesian product of A with itself. Now, we have already seen what we mean by a path connecting an element x to another element y in A. We recall that that idea. Suppose x and y belongs to A, we will say that x and y are connected by a path of length k in R. We say that x and y are connected by a path of length k in R. Well, if there are points A1, A2 and so on up to A k minus 1, all belonging to A, such that x related to A1, A1 related to A2 and proceeding so on up to A k minus 1 related to A. A k minus 1 related to y, Now, what we have seen that when we are considering a path in general, this path need not be through distinct elements, that is to say the elements ai's need not be distinct. In fact, these elements ai's have a special name. these are called interior elements of the path or interior points of the path. AIs are called the interior points. Of the path. Now, these interior points, as I have already said, may not be distinct, but what we realize is that we can always reduce any given path to a path containing only distinct interior points. For example, let us see this path, that is x. Let us suppose it goes to a point A1, and then from A1 let us suppose we go to A2, and from A3 let us suppose we go to A4, and suppose this is not A4, but let us call this A3, right. So, from A2 it will go to A3, right. Then it goes to A4, but suppose A4 and A1 are same. So, I have this, and then suppose this goes to a point A5, and then A6, and then let us suppose we ultimately reach y. Now, here in the sequence of vertices, A1 and A4 are same. Of course, what we can do is that we can cut this loop out, and we can have a path from x to y as x going to A1, then A1 to A5, then A5 to A6, and then to y. Now, it is not difficult to see that proceeding in this way, we can reduce any path to a path which contains only distinct interior points. This fact has got some interesting consequences when the set A is a finite set. Now, we have already seen that a transitive closure of a relation R, which is denoted as R plus, is essentially the union of R with R square, then R cube, and so on up to R to the power k, but we do not end there, we keep on going up to infinity. So, in general it is an infinite union of R j, where j starts from 1 and goes up to infinity. Now, this means that if we have two elements which are connected to each other by the relation R plus, suppose now these two elements are x y, then this means that there exists some, let us say k, such that k such that x r to the power k y. Now, this in turn means that there are intermediate points a 1 up to a k minus 1, all belonging to the set A on which the relation is defined, such that x r a 1 and so on up to x k minus 1 r y. Now, this we have already seen. Now, this means again that I can keep on reducing the number of interior points to the interior points which are distinct, and then if the set is this is finite, that is if A is a finite set containing n elements, a path with distinct element can be at most of length n, then a path with distinct elements can be at most of length n. Now, considering this fact, we have already seen that x r to the power k y will imply that x r to the power some I of y, where 1 less than or equal to I less than or equal to n, and this will mean that this x y, this pair is inside the union I equal to 1 to n of r to the power I. This in turn means that R plus is a finite union of sets in case A has size n. So, R plus is I equal to 1 to n R I, that is R 1, that is R union R square union and so on up to R to the power n. Now, once we have understood this, it is now clear to us that R plus will contain pairs of elements of A which are connected through a path of maximum length n having distinct interior points. Therefore, if we can find all such elements which are connected, then we have got essentially the transitive closure of R. This idea is used in Warshall's algorithm, which we are going to discuss very soon. But before that, I will recall again the direct technique that we have seen, that is to just get the matrix corresponding to R plus, which is essentially the matrix of R or matrix of R squared according to the special product that we have defined in previous lectures, then m r cube and so on and up to m r raised to the power n. This sum of powers of course gives us the matrix corresponding to the transitive closure, but the only problem is it is very difficult to compute these individual products and then take the OR of all these products. We will now move on to Warshall's algorithm, but we will first see an example. Let us now consider a particular set, which is the set containing 5 elements. So, this is A, we name the elements, let us say as A1, A2, A3, A4 and A5, right, and we take a particular relation which is given by A1 comma A1, then A1 comma A2, then A2 comma A3, then A3 comma A4, A3 comma A5, and lastly we have another element A4 comma A5. All right. If we check the matrix corresponding to R according to the ordering given in A, then this matrix is of this type. This is 1 1 0 0 0, then we have 0 0, then A2 A3 1 0 0, then we have 0 0 0, then 1 1, and lastly we will have 0 0 0 0 1, and the fifth row is all 0 because A5 is not related to anything. So, we have all 0 fifth row. In order to start Warshall's algorithm, we consider a sequence of subsets of A. So, the first one in the sequence is called S0, which is the empty set. The second one is S1, which consists of only one element A1, The second the third set is A1 A2, the fourth, that is S3 is A1 A2 A3, S4 is A1 A2 A3 A4, and lastly S5 is A1 A2 A3 A4 and A5. Now, corresponding to these subsets, we will construct relations. So, corresponding to S0, we have the relation W0, which is same as R. Then, corresponding to S1, we will construct a relation which we will call W1, which is, well, something that we will derive from R, and in a specific pattern iteratively we will keep on defining new relations W3 and W4 corresponding to S3 and S4, and then ultimately we will get W5 corresponding to S5, which we will claim to be R plus, that is the transitive closure of R. Now, let us see how we get from W0 to W1. Now, we define in this way that consider two elements x y belonging to A. Then this pair x comma y belongs to W1 if and only if x comma y belongs to W0 or x comma A1 and A1 comma y both belong to W0. This is very important, so we must have a close look at it. What I am saying here is that we are defining a new relation W1 from W0, and what is the new relation? So, given a pair of elements x and y, I should be able to say whether this pair, the ordered pair to be more precise, whether this ordered pair belongs to the relation W1 or not. I will say that x comma y, the ordered pair, belongs to W1 if and only if x comma y belongs to the previous relation W0 or there is a path connecting x to y through the set S1. So, this means that I have x over here and y over here, and there is a relation from x to A1, that is x r A1, and then x A1 r y, and we know that r and w 0 are same. So, we have a path from x to y. If this happens, or if x and y are directly connected through the relation r or w 0, whatever we say, then we say that it is in w 1. The question at this point is that how do we construct the matrix corresponding to w 1 based on the matrix corresponding to w 0. We see that the matrix corresponding to w 0 is same as the matrix corresponding to r, that is m r. So, I can safely write over here that m w 0 is 1 1 0 0 0 0 0 1 0 0 0 0 0 1 1 0 0 0 0 1 and 0 0 0 0 0. And then when I am constructing the matrix corresponding to w 1, well, I will put 1 at all the places where there is 1 in m w 0. So, I will put 1 in these two places and these are undecided, but of course, this is 1 and this is like this, and then I get these are undecided points, but of course, these are 1s, and then here we will get 1 over here, and in the last one I will write like this. Now, I have to decide whether to put 1 or 0 in, let us say, this position, that is first row and third column. For that, the corresponding elements are A 1 and A 3. So, I have to check whether I have a connection from A 1 to A 1 and A 1 to A 3. So, that means in the matrix m w 0 I have to see what is the entry of the first row first column. So, let us now write as a symbol these entries as Sij, this is a 5 by 5 matrix, and let us suppose by symbol I write this as Tij 5 by 5. So, I am to decide whether T 1 3 is 0 or not. For that, I have to check whether A 1 is related to A 1 and A 1 is related to A 3. Now, that means A 1 is related to A 1 is given by the entry S 1 1. If A 1 is related to A 1, then S 1 1 must be 1, and if A 1 is related to A 3, then S 1 3 ought to be 1 also, but we see that S 1 3 is not 1, but it is 0. So, this is not correct. S 1 3 is 0, therefore, T 1 3 is 0. So, we see that we have a rather simple rule. We do not have to really think much, we just put the entries 1 wherever it is 1 in the previous matrix, and for the rest of the entries we just write like in this case T13 is product S11 S13, and in this case it is 0. Therefore, I will put 0 over here, and if I go on like this, I will see that I will get 0 in the other places as well. So, if we consider T14, according to my rule I have to only check S11 and S14. S11 is 1, but S14 is 0. So, it is 0. So, I will put 0 over here, and then T15, right. So, please see that T15 is S11 and S15. S15 is this entry which is 0, therefore, this is 1 times 0. So, it is 0. So, I have resolved this. Now, if we go on in this way, we will find the other entries to be zeros. So, I will put all of them to be zeros. You can check that on your own. My intention of doing this is that I would like to see what happens in MW2. So, suppose now we have got MW1 and I would like to construct MW2, but first of all, what is W2? X comma y, right, belongs to W2 if and only if x comma y belongs to W1 or x comma y belongs or now it is a question of intermediate point. So, it is x comma A2 and A2 comma y both belongs to W1. So, if we now look at the digraph corresponding to this. So, suppose I have got x and y. So, there in W2, if there is a direct connection through W1. So, I do not have to worry about what happens in between, but possibly either if we reduce it even further, then there are two cases, either you have a direct connection from x to y or we have a connection from x to A1 and A1 to y. These are through the relation R. So, combining these two relations, I will say that x is directly connected to W1, and then the next possibility is that x is connected to A2 through W1, and then A2 is connected to y through W1. Now, each of these segments can be blown up to something like this. Right. So, you can have intermediate points, but this basically means that x is connected to y in such a fashion that the intermediate points of the paths are lying inside the set S2, which is A1 and A2. Is kind of straightforward, but this is something that goes on over and over again, and eventually when we come to Wn, then if two elements are in Wn, that means that they are connected through a path consisting of the elements in A as interior points, but well, that is all about getting the transitive closure. If we have a relation which connects two elements through that relation in whatever possible paths containing the elements of A, then that relation is of course transitive closure, because transitive closure is union of Ri's where I runs from 1 to n. Now let us see what happens when we want to construct the matrix corresponding to M matrix corresponding to W2, that is M W2. So, we have already got M W1 well. Let us write this matrix. All right, we have this matrix and we would like to construct the matrix corresponding to MW2. I am sorry, the matrix corresponding to W2, which is MW2. According to our rule, we are quite safe if we put all these ones wherever they are, right, and in place of zeros let us put small dashes. These are the positions that we have to fill in. And lastly, we must not forget the last row, that is all 0. Now, we start from here. This is right now T13. Please note that it is also quite reasonable to change the S and T symbol. Now, MW1 entries will be referred to as Sij's and MW2 entries will be referred to as Tij's. All right. So, now we are interested in finding out T13. Well, it is undecided because in MW1 it is 0. So, let us patiently try to find out all these elements, right. So, T13 is now S12 S23. Why it is S12? Because I am now interested in paths through the point A2. So, S12 is 1, S23 is also 1. So, it is 1, I will put 1 here. The next entry is T14. Let us compute T14, this is S12 which is 1, S2 4. S12 is this very special element now which is 1 and which is going to appear in many places, and S24 is the element here 24 which is 0. So, 1 into 0 it gives me 0. So, I will put 0 over here, and then in the next entry x15, this is S12 and S25. S12 is of course 1, but S25 is 0. So, I get 0. So, I will write 0 over here. Now, we come over here, this entry is this is T, this entry is T24. T24 is S22 into S24. S22 is 0, therefore, S22 is 0, therefore, I have 0. Now, I write 0 here, and then I come to S25, which is S22 and S25, which is also 0 because S22 is 0, and then I come to T of wait a moment, here S24, yeah, it is 0. So, S24, this is S24, this is 0, and 25, this is also 0, but we forgot S21 which is S22 and S21 which is of course 0, and we have T22 which is again S22 into S22 which is 0. So, I have got this as 0. Again, if we use the same way, if we compute the other entries, we will see those are all zeros. I am not doing that here, but I leave it as exercise. Please use this same way. For example, let us consider this element. What is this element? This is third row, second column. Now, that is this is T3 2. What is the value of T3 2? So, I have to simply write S32 and S22. Now, what is the value of S32? If we now check the matrix, we will see that S32 is S32, this is this entry which is 0, S22 is of course 0. So, again 0 into 0, so we get 0. Next, we take this matrix, that is MW2, and move on to considering MW3. We see when we compare MW1 and MW2, we see that there is only one change, that is the first row third entry has become 1 and rest are all same. So, now I will write down MW2 again and try to find out MW3. So, MW2 is 1 1 1 0 0 0 0 1 0 0 0 0 0 1 1 0 0 0 0 1, and the last row is all 0. Now, when we are considering MW3, well, before that, now change S and T's. Now, these are my Sij's, of course 5 by 5 matrices, and we consider MW3, well, whose entries will be denoted by Tij's. And I hope that we will see some action here, because up to this point we are saying that very few entries are getting changed, right. So, we hope that we should get something nice over here, that a lot of zeros should become ones. So, let us see whether it happens or not, but first to start with we will put ones wherever there are ones. So, I will get like this, and let us agree to put small dashes wherever we are undecided. So, we get something like this, and again put 3 dashes and then again 1 over here and a 1 at the end, and then we have got 1 2 3 4 dashes and a 1, and the last row consists of all dashes. Now, we will see what to do. Well, we will start with this entry which corresponds to T1 4. So, let us start writing T1 4 is S1. Now, what? We have exhausted 1 2 and now it is 3. So, S1 3 and S1 4. Sorry, I am wrong here, it is not S14, we have to consider paths which go through 3. So, it is S3 4. So, let me change this portion, right. So, we get here S3 4. Now, what are these elements? S13, well, this is S13 and S34, this is S34, both are 1s, therefore 1 into 1 is 1, therefore we put a 1 over here, and then we have T15 which is S13 and S35. Now, S13, well, we can lock onto this element for the time being is S13, we know that it is 1, and S35, well, it is the third row and we go up to this. So, 3 5, this is 1 again, so 1, so 1, so we will put 1 over here. I get a 1 here. So, the first row is complete. We go one step below to the second row where we have T 1 which is S23 and S31 according to our agreement, and now we search for S23 in the matrix. Well, this is the second row and we go up, we locate the point here. So, this is S23, we can safely target this one for the time being. So, S23 is 1 and S31, well, S31 is this one, so which is 0, so it is 0, so it is 0. So, we have got a 0 over here, and then T22, so this is S23 and S32 which is again 1 into S32, see this is S32 which is 0, therefore, we put a 0 over here. So, we get 0. Now, we come to the other entries, that is to the right of the 1 in the second row, and let us see what happens over here. We have got T23 which quickly gets translated to S23 and S33. Now, we search it's S23, we have already locked it, which is this one and this is 1. Therefore, we put a 1, and S33, well, S33, this is 0. So, I get 0 over here, another 0, and by the way, there is a mistake over here, it is not 3 because 3 is already taken care of from the previous matrix. So, I will cut this off, it will be in fact a change over here. I will cut this off, right. So, we have got T24, this is the 4th entry. So, we have got T24 which is equal to S24 and S, again it is not S24, it is S23, right. So, we will have S23 and S34, but that is something different because S23 is 1 and S34. So, we have to search here and we come to this point. This is S34, this is also 1. So, we get 1. So, instead of 0 here, we will get a 1. So, we will get a 1 over here, right. So, we go now to the element T25. This element is S23 and S35. Now, S23, as we have seen that it is 1, we have to search what is S35. S35 is this guy and this is also 1. Therefore, you have got 1 over here. So, you have got 1 over here, and again we now look at the remaining elements. Remaining are the remaining dashes, small dashes. So, what is this one? this one is T 31, T 31 is S, T 31 is S 3 3 and S 31. Now, S 33 is 0 because that is this entry. So, it is 0 into S 31, S 31 by the way is also 0. So, it is 0. So, I put a 0 over here, I know that it is 0. Then 3 3 2, that is S 33 and S 32. Please see that I really do not have to worry about what is S 32 because once I have seen that S 33 is 0, it is 0. So, I put over here 0 and T 33 which is again S 33 and then S 33, of course, this is 0. So, this is 0. Now, next we come to T 41 which is T 43 no, which is S 43 and into S 43 into S 31. So, this is S 43 into S 31. Now, what is S 43? S 43 is 0. So, I do not have to worry, is 0 and so it is 0 and whenever I am starting with T 4 and whatever it may be T 4, let us say T 4 I, this is going to be S 43 and S 3 I. Whatever is the value of S 3 I, it is 0 because S 43 is 0 because S 43 right. So, I come here, yeah, S 43 is 0. So, I do not have to worry, it is 0. So, that is why all these are zeros and see S 53 is always 0. So, we can in this context generalize a little bit. So, for example, now we are interested in finding out the 5th row and so in general it will be T 5 I and that gets decomposed into S 53 into S 3 I, but S 53 when we search over here, this is the element S 53 which is 0. Therefore, it is 0 into S 3 I which is equal to 0. So, we really do not have to compare each and every element in the last row, we can put all 0 over here. Now, we can do this thing another 2 times and if you do that, you will find that M W 4 is same as M W 3, our way of obtaining is same and same for M W 5, all are equal to M W 3. This is something that I keep as an exercise. Please see by using the same rule. Just remember that when you are trying to find out M W 4 from M W 3, put all ones and wherever there are zeros, for those entries the rule will be T I j equal to S I 4 S 4 j in case of M W 4 when S I j is not 1. So, if Sij is not 1, then the corresponding in the next matrix to get Tij, do this, and for MW4 Tij, corresponding Tij is the entry of MW5 now, and Sij of MW4, use this idea, right. So, this is for MW4 when Sij not equal to 1. So, if we do like this, so ultimately we will see that the matrix MW5 is indeed 1 1 1 1 1 0 0 1 1 1 0 0 0 1 1 0 0 0 0 1 and then 0 0 0 all 0, and we claim that this is equal to MR plus, and therefore, this relation MR plus can be written as see this is R plus, we can write from the beginning A1 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 A2 A1 A3 A1 A4 A1 A5, then A2 A3 A2 A4 A2 A5, then A3 A4 A3 A5, and lastly one element A4 A5, and that is all. This is the transitive closure of the relation R. Thus, in this lecture we have seen by an example how to compute transitive closure of a relation by using Warshall's algorithm. Although we have seen a particular example, you will see that it is fairly easy to extend it to a general case where A is a finite set A1 up to An, because then we have to just write the corresponding sets, the chain of subsets in A and corresponding relations, and then ultimately everything boils down to the to a way of getting one matrix after another up to the last one, that is Wn. So, ultimately we will come to the general rule to compute Warshall's algorithm, the matrices by using Warshall's algorithm. So, here let us see that at some point of time we have got W k minus 1, the corresponding matrix is M W k minus 1, and let us assume that the corresponding elements are Sij n cross n, and we write M W k as Tij's n cross n, then the rule is that Tij is equal to 1 if Sij equal to 1 and it is equal to Sik into Skj if Sij equal to 0. If you use this rule and keep on computing matrices and ultimately come to k equal to n in case the number of elements in A is n, the final matrix is going to be the matrix corresponding to the transitive closure of the relation that you are considering on the finite set A that you are considering. So, let us stop here for the time being. Thank you.